Okay, chapter 11 is on belts and chains. So basically we have, to start off with, we're talking about belts. And the main idea behind belts and also for chains is that they transmit rotary motion. And they could also transmit torque. So you could have the torque from a one part of your belt system go ahead and be transmitted to the other side, but also change the torque. So that's a useful aspect. And also, the main difference that we have between our belts and chains that are different than gears are the rotational directions, because we know for gears, when one gear is turning one direction, the other gear that it's connected to is turning the opposite direction. But for a belt or even a chain system, the two, we don't actually call them gears. We call them pulleys, or you can call them sheaves. They actually turn in the same direction. So that's most definitely a bonus when you're talking about the direction of the rotation. Also, we could pretty much use whatever distance. It could be really flexible in the distances between the centers of those pulleys or sheaves. So that's a very useful thing as well, because we can understand when gears are connected, there's not much distance between the centers, but we can most definitely transmit this motion over a larger or wider, longer distance. So some advantages of a belt drive, and there's more in the textbook, but these are kind of the main ones here. Cheaper than overall cost, you would say, is cheaper than a gear drive. That would be to manufacture it and to put it together, assemble it, would be overall cheaper. We have flexible shaft center distances, so that's very useful. And there would be overall less noise, especially when you're using the belts. We'll talk about chains in the second half of this lecture. Disadvantages is that belts will most definitely stretch over time. They're usually made out of a rubber-like substance, some kind of polymer. Slipping can most definitely occur, and they're not going to be as sturdy as gear drives. So there's some things that you might have to think about. Maintenance over the life of it is very important to consider. Now, the kinematics are very similar to what we did for gears. So there's something still called the velocity ratio. That will also always be the driver omega divided by the driven aspect omega. And you could also relate that back to the diameters. It's the second diameter, the diameter of the driven pulley divided by the diameter of the driver pulley. So be careful about the D2 over D1 versus the omega 1 over the omega 2. Could most definitely mess you up if you're not careful about that. Okay, so typically what you're gonna see is that you're gonna have a motor that would be attached to your smaller gear, and you would go ahead and have your D2, as you can see right here. That's your driven. I'm going to say gear, but you should be calling it a pulley or call it a sheave. So let's try to use those terms there. So we have D1 for the smaller pulley, and D2 for obviously the bigger pulley or sheave. Okay, and so you have to make sure that you understand which one your motor is being attached to, which would be your D1. Okay, and then something that to keep in mind is that there's a velocity of the belt. That's called the VB right there. And that velocity along the entire length of the belt is going to be exactly the same. So it doesn't matter what pulley it's close to, where the belt is close to, the VB will always be exactly the same. The omega 2, omega 1 are different, but the VB will always be that same linear velocity. Now we should already know this. The belt velocity is going to be equal to the radius of one of your pulleys multiplied by the omega of that pulley. And you could do this. R1 times omega 1 is going to be the same thing as R2 times omega 2, because we all know it's the same thing as VB. They both equal VB. So that's something to most definitely help yourself out with depending upon what information you're actually given. Okay, so we should also understand the omega in this equation will be rad per second, and we're talking about the radius of whatever pulley we're referring to. If I go back real quick, just keep in mind that this D2 and this D1 is the pitch diameter that we're referring to. So it's not exactly the diameter of whatever this circle is right here. It is the diameter, the pitch diameter, which is related back to something that we talked about for gears. Now, if you want to get feet per minute, well, then you would need the diameter, the pitch diameter of your pulley, and then the RPM. We're going to consider the N right here, but the RPM, which you're going to have to convert your omega into an RPM. Multiply that by pi and divide by 12, and you can get feet per minute. Now, the ideal speed range for a belt, okay, would be your between 1,000 feet per minute all the way up to 6,500 feet per minute, and that would be your ideal velocity for the belt drive. All right, there's three really what we call V belts, and you have a 3V, a 5V, and an 8V, and this has to deal with the cross-sectional area of the belt. Okay, so these pictures right here are just cross-sectional areas. The bigger the number, the bigger the cross-sectional area. So you can imagine that something that's really has a lot of cross-sectional area is going to be able to kind of have more energy applied to it, if you will. So we use this diagram right here where you see horsepower on the x-axis and RPM on the y-axis. So you could see higher horsepower and moderate RPMs, but just for larger horsepower, you're going to have 8V overall. It goes up to a certain limit in terms of the RPMs, but this is what you're talking about in terms of the range of horsepower to use. And for the 3V, you notice that small amount of horsepower, and obviously it goes up to, let's say, this amount all the way up to here, but that would be for larger RPMs. Okay, so you can really think about what's going on there in terms of using horsepower and combining that with RPM aspects. It doesn't go up to the larger values for the 3V. 5V, as you can see, is kind of in the middle range in terms of going up to a higher horsepower, also utilizing certain values of RPM. But you notice the 8V most definitely gets you to the farther reaches of your horsepower to your 1,000 here, but using a certain range of RPM for that. So you could consult this depending upon your design horsepower and how much RPM you have to go ahead and figure out what cross-sectional area you're going to use for your V-belt. Common strategies to use multiple belts. As you can kind of see in this picture here, you see multiple belts side by side, and that's going to prevent slipping from happening, and also shares the load. So sharing the load most definitely is going to be useful, so you don't wear out your belts as frequently. Now this little diagram here is just basically your available sheave pitch diameters. Once again, the diameter or the pitch diameter is a certain value related back to the size of your pulley, but for 3V, 5V, and 8V in inches, we have these pitch diameters readily available. All right, to avoid belt fatigue and vibrations, the center distance for between the two pulleys of your belt system should be between, so on the lower end it would be the pitch diameter of the driven pulley, and on the upper end it's 3 times the summation of the two pitch diameters. So that's where we would consider the sweet spot for the length between the center distances of your pulleys. Now the length of a belt takes into account the center distance, takes into account the D2 and the D1, as you can see here, and here's another C value as well. And so that would be the overall derivation of the length of your belts, depending upon what your pulley sizes are and the distance between the pulleys. You could kind of solve for the C value if you wanted to, depending upon the diameters, the pitch diameters of your driven and your driver. And this B value utilizes the length of your belts and also obviously the diameters here. Okay, so you can think about this as another way, or a backwards way to solve for your design parameters. So utilizing these equations shouldn't be very difficult. Just takes a little bit of patience to go ahead and plug and chug. But these would be how you would get the standard lengths of your belts. So available 3V belt lengths, 5V belt lengths, and 8V belt lengths are given in these tables right here, and these would also always be in inches as well. All right, getting into chains, which is very similar to belts, but chains do have their advantages over belts, is that they're less likely to slip than belt systems. Once again, they also have flexible shaft center distances, and they're also more effective at lower speeds. So lower speed chain drives, drives are going to be more suitable for chains. And this is where we can actually get a relatively large amount of torque to be applied and to be transmitted as well. Now, disadvantages, we see that lubrication would be needed. If it does slip, there's a complete failure, so that's not a good thing. And then there are many components that make up a chain, and that's something that you have to be careful about. So if torque is placed in the wrong direction or a certain amount of force, then you could destroy that chain, and you would have to get a completely new one. Now, the velocity ratio is exactly the same as what we have been referring to. Velocity ratio is the ratio of your omegas, omega 1 over omega 2. You have diameters, d2 over d1 again. And now you can get back into the number of teeth, because these guys, we don't call them gears, we call them sprockets. I'm sure you've heard of that before. They're kind of like gears, but we can see the sprockets, these teeth, they fit into the holes of the chain. So that's the main difference that we would have. We wouldn't want to say gears, we want to say sprockets here. So this VC is going to be the linear velocity of the chain. We see omega 1, omega 2 going in the same direction. So very similar to the belt system. It's just that we have these sprockets that allow the transmission of the motion. All right, so same equation going on. Chain speed is your radius, pitched radius, multiplied by the omega of your sprocket. And to get to feet per minute, it's still pi times diameter in inches, pitch diameter, times the RPM, which you would have to convert your rad per second into RPM, all divided by 12. So the ideal speed for a chain drive is going to be 2,500 feet per minute, which, as you notice, is less than what we have for the belt drive. And the chain speed is going to dictate the suggested lubrication. So for manual, which basically means no, or I should say no, which means you're applying the lubrication by hand, basically. You can think about a bike. Typically, people that maintain their bikes, so they'll lubricate it every time they go out. So that's not a consistent lubrication method. It's just every time you use it, right? So manual, less than 650 feet per minute. A bath, where you can imagine that the chain goes in and out of a bath as it's being used. That's between 650 and 1,500 feet per minute. And then a stream, where it's essentially like a shower of lubrication is hitting the chain all the time, well, then that would be greater than 1,500 feet per minute. So some kind of vocab that you have to take into account is that we have something called the pitch. Now the pitch is a distance between the pins of chain link. So if you can imagine, and basically that's where the sprocket tooth is going to go ahead and fit into the hole of the chain there. But the distance between each pin to the next pin is going to be called the pitch. Now, we use these numbers here, 40, 60, 80, to represent what we call the chain number. So we've got to be careful here, right? So the pitch is a distance, but if we said 80 as the chain number, that just means 80 times 1 over 80th, or I should say 1/80th of an inch. So if you can imagine, if we have a chain number of 80, multiply that by 1 over 80, and you get 1 inch. Right? So if it's 60, multiply by 1 over 80, and you get 6 over 8, or 3 over 4, and that would be 0.75 of an inch. And 40 would be half an inch, and that would be the distance between the two pins. So keep in mind what these numbers mean. The chain numbers multiplied by the actual pitch distance, and that's going to be what your actual sorry, let me take that back. That's going to be what your chain number is when you multiply 80 by the pitch. But if you actually want to get the pitch value, well, then you would go ahead and take the chain number and divide by 80. And you can go ahead and select a certain pitch for your particular roller chain. So in this particular sense here, and it says we're picking a particular pitch, but we're really referring to a chain number. As you can see, all these numbers are 80 or 100 or whatever they are, but those will be chain numbers there. All right, so depending upon your horsepower, depending upon your RPM, all right, then you can go ahead and choose a chain number that's going to go ahead and suit your needs. So very useful aspects that are going on there. So just keep in mind that all these numbers here refer to that number times 1 over 80 to actually get the pitch value of your chain. All right. Now a sprocket has, as you can imagine, an integer number of teeth, and this chart just basically tells us what's the commercially available sprockets that exist out there. All right. So depending upon the number of teeth that you want and the chain number, you can see right here, the X's mean that they're available. So you can take a look at that on your own time. The pitch diameter of a sprocket does depend upon the number of teeth. So first of all, you take the pitch, which we know is in inches, and you don't want to do that chain number. You want to do the actual pitch in inches, divided by the sine of 180 divided by the number of teeth, and that's going to be your pitch diameter. Okay, so that's how you would actually find that value there. So go ahead and find the, or to talk about the chain length, right, to avoid that sag and fatigue as we would do with a belt, but now for a chain, we want the center distance to be between 30p and 50p. So 30 times your pitch, and less than, so greater than 30 times your pitch and less than 50 times the pitch, to go ahead and be your center value, distance between the two sprockets centers. So it's something to keep in mind as we go forward. All right. Something else to refer to here is that the length of the chain is going to be based upon that center distance. It's going to be based upon the pitch of your chain, the number of teeth that both sprockets have, N2 and N1, and here's the center distance again. So we have this length of the chain based upon all these number of teeth, the center value, the center distance value, and the pitch. And then you also have to think about the chain must have an integer number of links, something to keep in mind there. If we want to find the center distance, we can kind of go in a reverse way. If you know the length, if you know the number of teeth, if you know the pitch, number of teeth again, you can go ahead and find the center distance between the two sprockets. So keep in mind that these equations will be given to you if you need to use them to find length or to find center distance. So it's just a matter of plugging and chugging and